Hello everyone, welcome to our talk on how machine learning can help reduce rig downtime from problems such as stuck pipe. My name is Tim Robinson. I am a data scientist at Exebenus. Exebenus focuses on machine learning tools for drilling and completions, as well as digital operating procedures to replace more traditional document-style instructions. Outside of oil and gas, I've applied machine learning in a range of project areas, including financial services, targeted marketing, and counter-extremism. In this talk, we will introduce machine learning and motivations for its use in the oil and gas industry. No prior knowledge of machine learning is needed. We'll cover cases of stuck pipe prevention as a focus topic. To wrap up, we'll explore more high-level considerations for applying machine learning and better utilizing existing investments into data assets that your organizations may have. Let's kick off with a quick intro to machine learning and how it's useful across many industries, including oil and gas. Machine learning, or ML, refers to a set of mathematical and computational methods for building models which learn from data or past experience. The parameters of these models are inferred from what we call training data sets, rather than being explicitly defined. This means that ML models can perform tasks without being explicitly instructed on how to do so, such as regression, classification, generative modeling, and exploratory data mining. This contrasts with physical models that you may already be familiar with, for example, the Norse Open Lab drilling simulator. Now, while these can be excellent tools, their parameters must be defined ahead of time based on theory or empirically, and this can be challenging. Machine learning models therefore provide a complementary toolset to us. Machine learning underpins powerful tools used across a variety of industries for many applications, many of which we may even use on a daily basis, including facial recognition for unlocking a smartphone, virtual assistants and chatbots, machine translation, maybe even targeted marketing, and credit scoring and fraud detection, to name a few financial examples. You may also be familiar with personalized recommendations on services such as Netflix, or even TikTok for those of you who are young enough for that. There are many use cases for machine learning within the oil and gas industry, such as predictive maintenance applied to rig equipment, operational optimizations, for example, applied to ROP optimization, as well as risk detection and mitigation, which might include detecting early signs of well control issues or stuck pipe. We have chosen to focus on stuck pipe for this presentation. It's a high-cost issue, and it can be a major source of non-productive time, as well as a serious drain on finances. Stuck pipe is common enough and costly enough to be a critical drilling problem. Various estimates indicate that stuck pipe costs the industry in excess of $250 million per year. This is from a study between 1985 and 88, compiled for 700 wells drilled. If we adjust this for inflation from 1988 US dollars, this would exceed $560 million in today's money. Now, complications related to stuck pipe can account for nearly half of total well costs, and this makes stuck pipe one of the most expensive problems that can occur during drilling operations. Now, stuck pipe is a possible risk in all types of wells, vertical and horizontal. It's not just a risk in drilling, it's equally possible in completions operations. So in other words, stuck pipe is a risk at all stages of the operation, from exploration to appraisal to development and production. In some cases, a stuck pipe can be relatively minor and resolved through working the pipe mechanically or rotating it and perhaps circulating to clean the hole. In others, the issues can be severe enough to require a new sidetrack to be drilled, or perhaps in some cases even abandoning the well entirely. Let's now go through some real-world case studies of machine learning applied to early detection of stuck pipe risk. For this, we'll use our product Exebenus Current ML. The following examples will cover tripping operations as well as reaming operations. Exebenus Current ML can be used to provide early warnings relating to stuck pipe risk. For context, it's a cloud-based solution that takes in real-time input data as WITS-ML and also provides outputs again as WITS-ML. There are three ML modules, or termed as agents, which monitor risks of differential sticking, wellbore geometry, and hole cleaning problems. These are three issues which are key and linked to stuck pipe. The machine learning agents predict parameters of interest ahead of time based on recent sequences and analyze the predictions for abnormal patterns which could be indicative of problems. The differential sticking and wellbore geometry agents focus on drag increases manifesting in the hook load measurements, while the hole cleaning agent estimates downhole equivalent circulation densities, or ECD for short, based on the surface data. Raising warnings ahead of time provides the rig crews an opportunity to take corrective actions and potentially avoid the stuck pipes. So in these case studies, we run the machine learning system on historical data in pseudo-real time. We then visualize the Exebenus current ML outputs in Kongsberg's Sitecom Discovery web viewer, a sample of which we can see on the right-hand side here. And we also show the data from the normal surface sensors from the mud loggers. Now, predictions ahead of time, which are the red curve on the right, are not a literal roadmap of expected behavior. Instead, these variations in trend in these curves are used to identify abnormal behaviors. The past predictions are shown via the green historical curve, which is on the left-hand side of the image. Warnings and alarms are shown in the status bar track as yellow and red respectively, green showing that there's no actual problems. The annotations that you can see are also automatically generated. Now, it's worth noting that the warnings appear at the time the prediction is made rather than at some specific time in the future. It's also interesting to note that the lead time from warnings to stuck pipe incidents can be quite variable, as the whole conditions are often very different. In some cases, the warning signs may appear shortly before the problem, for example, if there are cavings or other types of wellbore instability. In other cases, there's a long, slow build-up of problems, with small changes that are often not noticed by the rig. So let's look at our first case study. This is tripping in with a 5-inch liner, where some warnings appear before restrictions. Now, the block position is the black curve we can see in the upper track. In the second track, we have the measured hook load, which is the blue line, together with the predicted breakover hook loads, which relate to static friction and drag. Now that's the green dotted line. We can also see warnings and alarms from the differential sticking agent as yellow and red lines with text annotations, raised before the incident actually appeared in the data. So these warnings were raised by the differential sticking agent before the restriction. And here the rig crew needed to wash and work the liner down further, culminating in a failure to actually set it. This led to an undesired clean-out drilling run and many days of downtime. Okay, let's move to our second case study. Here we have a stuck pipe occurring during reaming because of a pack-off. So the location of the pack-off is shown by the first arrow on the image here. And we can also see that warnings were raised by the hole cleaning module before the incident. In the upper track, we have hook load measurements, and in the lower track, we have estimates and forecasts for downhole ECD. Just to remind you, the system analyzes the variation in forecasted values for raising warnings. Two sets of warnings are raised here, the first appearing roughly an hour ahead of the incident, and the second one about 30 minutes ahead. A long jarring period followed this pack-off, culminating in many days of non-productive downtime. So lastly, let's cover this third case. Here we have predictions for a tripping out interval where multiple restrictions were encountered at the different labeled points we can see in the image. Several warnings were raised by the differential sticking agent prior to each restriction, as we can see by the messages shown on the display. This resulted in delays where the drill string needed to be worked mechanically to free it off, but didn't require any kind of huge periods of downtime of many hours or days. So a quick note on some related work using these tools on live operations with our partners. There'll be 3 papers relating to stuck pipe prevention presented at the IPTC 2021 conference in March. And this will be by Exebenus as well as our partners from Petronas and Phasmiar. Let's now pivot to explore more generally about how machine learning can be incorporated into organizations within the oil and gas space, building on the existing assets that many of you will actually possess. We will consider characteristics of data needed to support such projects, as well as limits on the general applicability of machine learning models. So, once an application or a project has been identified, there are 3 very useful questions to ask to help guide your thinking. Firstly, is there sufficient data available to support the proposed work? Second, if the data is available, is this representative of the processes which you're trying to model? And thirdly, once you've fitted some models, Can they actually generalize well to previously unseen data examples? Let's now delve into these questions. To support a real-time analytics system, data must be consistently available in real-time live settings. There's no point building models on historical data using variables that are not actually available operationally, even if they seem to boost performance in your historical tests. We must pick input variables that are actually practically obtainable. The information content of data is also key. A high sampling frequency captures greater detail, and if you can get it, minimal processing applied by the service companies is preferable. For example, the processed and smooth data that you can see in the hook load graph on the right-hand side here is not as useful as the raw data, as it's lost specific interesting features such as the break over hook load, which, as I mentioned earlier, relates to the force required to overcome static friction. So raw data, it may contain measurement noise, but this can actually be managed as part of your data pipeline. The processing steps that people may apply are often irreversible, so you can't get back this information once it's been discarded. So let's cover our second question. A smaller quantity of representative data is more useful than a lot of poor data, so I'll explain what I mean by that statement. If all of the interesting effects and phenomena that you're trying to model are contained within a small yet representative data set, this will probably lead to better modeling outcomes than using a huge noisy data set that only covers a subset of the information relating to the process of interest. So why is this? We cannot expect machine learning models to work well in situations they've never previously been exposed to. And this really comes from the fact that machine learning models are learning from past experience. With no past experience of something, nothing can be directly learned about it. So for example, if you're seeking to model downhole circulation densities in high pressure, high temperature environments, a model trained on low pressure, shallow, low temperature data probably not going to work very well. So we want to capture as much useful information as possible in our data sets. However, this is not always fully achievable. Sometimes missing information may not be practically observable, and this will lead to greater prediction uncertainty and errors, both systematic and random, depending on the situation. So let's consider a supervised learning example. So we want to model a deterministic process, which we say can be represented by the function f, mapping x1, x2, and x3 as inputs to y. However, what if some of these variables are not actually observable? This means in practice we have function g of x and x1 and x2 with a seemingly unpredictable component epsilon that results in a greater uncertainty. So this doesn't mean that model G is not useful in this case, just that we should be aware and understand that these models have limitations. Okay, so ideally we want to have generalized models. This is that third question that I initially asked. A generalized model can be applied out of the box to new data. So that new data may be new wells, new reservoirs, perhaps new regions. And these generalized models should be able to provide value immediately. This in practice means low prediction errors on new data that's been, or I should say, has previously been unseen by the models. This thus supports plug and play usage and removes the need for any offset well data. However, as we discussed previously, there are some limitations to this, particularly if there are any fundamental shifts in the data or unobservable factors. So, something that's very important of a generalization is the strategy for splitting the data sets that are used for training and validating models. Where possible, it's good practice to ensure maximum independence between the training, validation, and testing data within the scope of your problem. This encourages models to learn quite general features and patterns, particularly when the training process itself, the optimization process, depends on the performance on a validation data set. If you train and validate like this, you can typically be much more confident that a model will perform well on new data because it's both validated then tested on what is new data. So finally, let's consider how all of this fits together into a real application. As I mentioned earlier, many companies have already invested in things like real-time data infrastructure, monitoring centers, and communications protocols with the rigs. However, these resources are often underutilized. Our philosophy at Exebenus is to build tools which integrate with these existing assets with minimum effort needed from the users. Exebenus Current ML plugs into these WITS-ML databases, so an extra display in the real-time operations center is the main addition that you would need to get started. To summarize, machine learning can provide easy-to-use tools that help you realize operational improvements, reduce downtime and cost savings by more fully utilizing your existing data assets. It can augment your monitoring teams and strengthen existing work processes and workflows between the office and the rig sites. Thank you very much for listening, and we really look forward to your questions. If you're listening after the live event is finished, please get in touch via email with me, tim@exebenus.com.